Gresham College presents Stardust by Professor Carolin Crawford, Gresham Professor of Astronomy.
Hello everyone. I'm here today to talk to you about stardust, which is one of the perhaps less glamorous components of our galaxy and interstellar medium. But as you'll discover, it's a surprisingly important one because it's involved in several physical processes going on within our galaxy, and it's particularly important for the process of star formation and planet formation. And dust is everywhere in our galaxy. If you look at a spiral galaxy like our own, you have these dark drifts in between the stars that just kind of trace the spiral arms of the galaxy. Now, those are not absences of stars. Those are dark clouds of intervening matter, and there's dust mixed in with the gas, and it's blocking out the starlight. So it's on these huge scales within a galaxy. It's embedded with the gas in some of the nebulae within these spiral arms that we'll see, and it also comes down right deep into our solar system. So, for example, it forms one of the tails of comets as they fly through the inner part of the solar system. And when I'm talking about dust, let's be absolutely clear that obviously this is not household dust. Don't know how that would get into space. The other thing to be clear is I'm not talking about dust in the sort of Philip Pullman sense of the matter, which is the name he gives to dark matter. When I'm talking about dust, I'm talking about tiny solid particles, particles that are carbonates and silicates, so in other words, soot and sand. And these will be individual grains that are of the order of about a tenth of a micron across. And these are tiny solid grains. And sometimes they form aggregates to form larger clumps of grains in dust clouds, and these are bits of stardust, and you'll see how we get these a little bit later on. So you have the solid grain, and if it's in the deep freeze of outer space, it's often covered with a mantle of frozen ices, so things like water, carbon dioxide, ammonia ices, just coating the surface. And as I say, sometimes they stick together to form larger, sort of fluffier clumps of matter. And all of this is mixed in with the gas within the interstellar medium. So I want you to appreciate how small these individual grains are. If I tell you it's a tenth of a micron, that is 1,000th of a human hair across. It's about the size of the particles, say, in cigarette smoke. These are minute particles, but you can imagine if you have a gas cloud that's some light years long that's got the dust mixed in, there are enough solid particles that it can be completely opaque and it can mask the lighter background stars. However, it's not always apparent that dust is there. There is not that much there in terms of mass. If you look at a galaxy like this, if you count all the mass in the stars and the galaxies, the dust particles account for only about 1,000th of that mass. So it supplies about 1,000th of what we call the baryonic, or the ordinary mass within a galaxy. So it is, by mass, a very small component of the interstellar medium and of the whole galaxy. But again, you have big enough drifts of it, it can be completely opaque and obscuring. So the role of dust took a long time to be recognised, let alone what effects it had in our observations and the deductions we might draw from those observations. And I would say it's only really within the past few decades the role of dust as an important ingredient of our interstellar medium has become accepted. And even with the unaided eye, when you look at the Milky Way, you can see it's got dark clouds within it. There are patches that interrupt the starlight. But it was never obvious to early astronomers that those were actually not just deficits of stars. In fact, they called them, they regarded them more as holes in the sky. These are places where there aren't so many stars, which seems a reasonable enough understanding, but it did affect their results. So, for example, if you go to someone like Sir William Herschel, in 1785, he tried to make an estimate of the size and shape of the galaxy, and he took like 683 different directions out from the sun and counted how many stars he saw in each direction. And from that, he constructed this idea of a galaxy, which isn't bad, really. He's put the sun at the centre, which is a mistake, but he's still got the idea that it's a flattened distribution of stars. But he didn't realise that if there were few stars in one direction, he thought it meant you were looking out of the galaxy. Well, in some cases, it means you're looking into the galaxy, and there's just a big cloud of dust that's obscuring the background stars. And so he's got the assumption that the sky, well, the interstellar space is both transparent and empty, which it isn't. There were also mistakes in terms of assuming all stars with the same luminosity. That if a star is faint, it's because it's a long way away, where in fact we know we just get very dim stars. And so if you see a dim star, maybe it's a long way away, maybe it's just a dim star, or maybe you've got a big cloud of dust in front of it blocking out the light. And these kind of effects on observations weren't really apparent until probably the end of the 19th century. So in the late 1800s and early 1900s, the American astronomer E. Barnard was the first one to use astrophotography to map out these gaps between the stars in the Milky Way. And he was the one that really came up with the idea that these were clouds of intervening matter rather than holes in the sky. So this idea began to gain acceptance, but again, it wasn't really appreciated, the detrimental effect this had on observations, until probably the 1930s even, when the astronomer R.J. Trumpler was looking at open clusters of stars. Now, if you have a galaxy like our own, you've got these brilliant blue star clusters that dot the spiral arms. We live in one of those spiral arms, and he was measuring distances to these blue star clusters as a way of mapping out the shape of the galaxy. He measured the distance to the star clusters from two different ways, and what he realised was that the more remote galaxy clusters were far dimmer than they should be. They had, all the star clusters had the same kind of stars in, they should be the same intrinsic brightness, but they were far dimmer than just the distance alone. And that's when he realised you've got this thing that we call extinction, just the blocking of the light and the dimming of the light from the stars. So if you look at a cloud of gas and dust in space, here's a very famous one in Orion. It's called the Horsehead Nebula, or as some children I was teaching the other week like to call it the Loch Ness Monster Nebula. And you can tell there's a dust cloud there. You see the large number of stars up above here. This is the edge of the cloud where there's gas that's being burnt off and excited and it's radiating pink. But here there are fewer stars because the dust cloud is blocking out the background stars. If we zoom in around the Horsehead, you can see that in places it's completely opaque. You've got the background light of the gas here. And from looking at this image, you can tell several things immediately. First is there's a working edge. This is a very sharp edge. This is all kind of loose and fluffy. You've got starlight, you've got star winds radiating down from somewhere above the ceiling. They're eating into this cloud. They're steadily eroding the cloud. So dust gets blown off and gets burnt off. The clouds get eroded. You also see here a young star just breaking out of the dust clouds. And that's your first indication that dust clouds are where star formation takes place. And you can also observe one other thing that R.J. Trumpler noticed about his observations from distant star clusters, which is that when you do see starlight through a cloud, its colour is affected. Compare the light of the stars out here, where they're outside of the cloud, to the ones that you see through the cloud. The ones that you see through the cloud are redder. They've lost their blue light. And this is due to a process called Rayleigh Scattering. Effectively, if you have a star and the Earth, not to scale, obviously, and we have an intervening cloud of dust that occupies the space between us, the light from the star has to travel through that dust to get to us. And you have actual physical interactions between the photons and the dust particles within the cloud. And they scatter the photons. But it happens such that photons of light, are most efficiently scattered by grains that are larger or about the same size to them. So you have, in terms of the colours of light and their wavelengths and the size of grains that you get in interstellar matter, you find that blue light is preferentially scattered over red. And what this means is you have all the colours leaving the light, but the blue one gets redirected. It was travelling towards you. It's now just got scattered out of the way, and only the red light makes it through the cloud towards you. You've lost the blue light. Now, this process is one that we see in our everyday lives. Sunrise, sunset. The sun is red at sunset or sunrise because it's lost the blue light, and it's because of the scattering process from molecules and particles in our atmosphere. When you look at the sun overhead, again, not to scale, When you see the sun overhead, you're looking through less of the atmosphere than when you see it on the horizon at sunset or sunrise. Not only are you looking through a deeper depth of the atmosphere, you're looking through a denser part of the atmosphere, closer to the ground, and more of that. So you get more scattering and you lose the blue light. And so, as Chumpler discovered, dust clouds don't just extinguish the light of the star, they can also alter its colour, and this is called reddening. It's not to be confused with reddening from Doppler effect because something's moving away from you. It's a different effect, and it's just due to this intervening matter. So it's something you see within our galaxy. The other thing to realise is it's a very subtle effect that you cannot detect with the unaided eye. It needs to be telescopic images really to start picking up this subtle reddening. And it doesn't just happen with stars. So, for example, here are two nebulae, large hydrogen gas clouds glowing pink. They look like they're side by side, but the one on the left is twice as far away as the one on the right, and it's just seen through more of a dust screen, and it appears even redder, even though they're giving off the same original colours. And so reddening can affect not just individual stars, but large gas clouds. And there's another effect of this scattering. If you think again of the sunlight coming through our sky, this blue scattering gives us our blue sky. That was just in case you'd forgotten what one looked like. Okay? So you're here, and when you look towards the sun, you see all the colours of the sun come towards you. However, when you look up into the sky, you are seeing that scattered blue light that's been sort of shone in every different direction, and it then fills the air. And that gives us our blue sky. And in the same way that this blue scattering renders the invisible atmosphere apparent to our eyes, the blue scattering by dust can also make the dust cloud appear visible where it wasn't apparent before. So imagine you have a star where you don't have the dust directly in front, obscuring it, dimming it, reddening it, but it's still got dust clouds round. And those dust clouds are still scattering blue light. So if you were looking this way, the star would be reddened. But because we're looking this way, we just see that scattered blue light. So for example, here is the Iris Nebula. You can see the dust cloud trails along here. This is about 9 light years or so of dust. It's obscuring, it's dark. But as soon as it gets near this star, you've got the blue scattering that produces this Iris Nebula here. And the star's not hot enough to excite the gas and make it glow pink that the dust is embedded in, but you see this reflected, this scattered light. And these create reflection nebulae, and these are another key ingredient in optical wavebands that you've got dust present. So, for example, some of you may know the Pleiades, the Seven Sisters star cluster. That's blue because the stars are very young and blue, but they're also passing through some dust clouds, and you've got the scattering of the blue light, which makes them look bluer than they would have done. It also gives us the beautiful nebulae here, right next to the star Rigel and Orion. Orion is covered in dust and gas clouds. This nebula is known as the Horsehead Nebula. Hope you can see her profile. There's her hat and brim, nice nose, mouth, witchy chin. There you go. So we're revealing the dust by this scattered blue light. So you know the dust is there because it dims and extinguishes the light. It reddens the light. The other thing about dust is that you can actually directly detect it. So it's blocking the starlight from entering the cloud because the dust grains absorb that energy of the starlight. This heats them up just a bit. So from a few degrees above absolute zero, they get heated up when they're blocking lots of starlight to temperatures maybe tens, hundreds of degrees above absolute zero. Now that's still quite cold, but things at those temperatures radiate strongly in the infrared, in the same way that you are all radiating strongly in infrared at the minute because you're about the same temperature. And dust clouds near stars that are absorbing lots of energy, they radiate in what's called the mid-infrared wavebands. And this is something that we've only really recently begun to detect in great detail, sort of 1980s onwards. And with the advance of infrared detection, we can begin to actually detect the light from these dust clouds. So here you can see there's a dust cloud. Again, more stars at the top, fewer stars below. You can kind of make out the edge of the dust cloud along here. If I switch to the same picture now, but with infrared eyes, you will see the dust that's buried and hidden from our sight. Oh, that's good. A few oohs there, that's good. And so the dust becomes incandescent. You can see the structures. You can see these vast pillars of dust where they're being warmed. And you can play this game, nebulae like this within our own galaxy. You can also play it with external galaxies. Here's a spiral galaxy like our own. This is the Whirlpool galaxy. In optical, and then if you view it in infrared, the stars are too hot. They're not going to give off much infrared light. But the grains, the dark drifts along the spiral arms, suddenly become luminous. It's like you turn the galaxy inside out and you only see the dust grains. So the dust can actually be studied in its own right, and from the properties of the infrared light, as you'll see, you can tell something about what the dust is made of. When you have a spiral galaxy, I told you that the dust is only about 1,000th of the total baryonic mass within that galaxy. However, because it's absorbing all this starlight and it then re-radiates it, it absorbs from 1/3 to 1/2 of the total starlight in a galaxy to then re-emit it as infrared. So you've got something which is 1,000th of the mass of the galaxy. It's actually producing like 1/3 to 1/2 of the total light if you summed up all the light in all wave bands. So the dust is reprocessing a lot of this luminosity of the stars and energy of the stars. But there's another thing that's quite nice about the infrared wave bands. You've got the idea of scattering, that blue light gets preferentially scattered. Well, if you've got a really thick dust cloud, even the red light gets moved out of the way. And only the infrared, the very longest wavelengths, make it through to our eyes. So imagine you've got a little star cluster deeply embedded within one of these nebulae. Only the infrared light from that star cluster makes it through the dust. So if I just go back to this image that we had earlier, regions of star formation are not obvious here, but I want you to look around here, I want you to look around here and around here, and as we move to the infrared, you will see those embedded star clusters deep within the cloud. So the infrared allows us to see through the dust, or rather it allows us to detect the infrared light that's made it through the dust, and we can begin to see star clusters deeply embedded, where they are just forming within these dust clouds. Excuse me. So where does this dust come from? If we look at a galaxy, it seems to be confined mainly to the spiral arms and that flat disk. And I've shown you face-on spiral galaxies. As you can see from this one, edge on, there's so much dust in that disk, it almost seems to like cut the galaxy in half. Now remember, of course, we live in a galaxy like this. You live about halfway from the centre to the edge in that plane, in that disk. That means that we have a very similar view of our galaxy. So, for example, if you were lucky enough to view it from Australia, here's the centre of the galaxy, but you've got all this region obscured by these dark dust clouds. And you can see, I remember, a lot of these with the unaided eye, but again, particularly from the southern hemisphere. So the dust is a problem because it obscures some of the most interesting areas. If you only dealt with optical astronomy, you wouldn't see regions of large star formation that are going on in the spiral arms around us. It also completely obscures the centre of our galaxy. And so if you want to see what's going on right in the core of our galaxy, you have to use infrared light. If you want to see the star formation occurring within the deep dust clouds, you need to use infrared light. And that's why a lot of modern telescopes are moving to more infrared detection for trying to understand these hidden areas of our galaxy. But the fact that the dust is confined to this disk and where all the active star formation is going on gives us a big clue that the dust comes from stars. And in fact, it's thought to originate in the atmospheres of red giant stars. So a red giant star is a star at a very late stage of its stellar evolution. The centre is still burning fuel at the centre, but it's nearing the end of its life. The outer layers puff up and swell up, and the outer layers become actually quite loosely bound by gravity. It's so distended, they're not very well gravitationally bound from the star, and the star tends to be a bit unstable, and it gives off a lot of material in a massive wind. So it could be like a million times more mass than our sun, for example, gives off in its sort of solar wind. You get huge puffs of material coming from these objects all the time. So you're losing the outer layers of the star all the time. Not only that, but it's within these outer layers where the temperature, you need a reasonably cool environment to form dust grains. And you need the presence of some of, obviously, the relevant elements such as carbon and oxygen. And they tend to be have been processed in the core of these stars, or they were incorporated in the star in the first place, but it's in those outer layers where the right chemistry happens. And perhaps a good analogy here that to make would be it's like the formation of soot in a candle flame. You've got carbon and dust that's generated within the outer layers of the star and then loosed off when the star undergoes this instability and gives off these clouds of material. So one very nearby red giant, for example, is Betelgeuse in Orion. You may not realise it. This is a picture of Betelgeuse. Right in the core here is the star. You probably can't see it, but there's a little red circle here that gives you just the diameter of the star. Now remember, this is a red giant. If you plonked it in our solar system, its outer radius would be kind of out to Jupiter. It's about 5 times the Sun-Earth distance. But Betelgeuse is giving off material all the time, and it's surrounded by this enormous dust cloud. This is a picture in the infrared, so it's false colours, and this extends out sort of 80 times further. So it's about 400 times the Earth-Sun distance. And it's just, you've got the star, and it's given off all these clouds of gas and dust, and it's surrounded by this shell. And many, many red giants have got these large clouds of dust around them, and so they're puffing it off all the time. You've got Betelgeuse. This is the brightest, one of the brightest mid-infrared sources in the sky. It's a star called CW Leo, and you can see, again, infrared picture, but you can see shells of dust surrounding it. So it's given off various bursts of, it's erupted in various events that have caused these expanding shells of material to be stretching out. And the star is embedded right within these layers of dust. And that gives us a chance to find out more about what the dust is made of. And, so when I'm quite blithely telling you it's carbonates and silicates, in other words, soot and sand, we have good reason to think that. First of all, these dust shells surround a warm star. They absorb the energy from that star, and they will glow, they produce the infrared light. Now, if you have we don't just use images in astronomy, we use spectra. And you can have signatures in the spectrum indicative of certain elements or certain compounds. So I'm afraid the next slide's going to be bright, just to warn you. But for those of you who are spectroscopically minded, what we have is colour along the x-axis here. We have the intensity of light. And so it's just the distribution of colours. It's the spectrum of the star. All I need to show you is that there are bright peaks at 10 and 18 microns wavelength. That's characteristic of if you have sort of silicates, so silicon-oxygen bonds, stretching or moving and rotating. They give off energy at these particular things. It's a characteristic of silicates. You see them where the grains have been warmed up and they're giving off this emission. You also see them where they absorb the light from the underlying star, and so you also see them in absorption. And so from stars like this with their shells, we know quite in detail about the composition of the dust. Around carbon-rich stars, you don't just have silicon, you also have features, say, for example, this is silicon carbide. You've even got ethane here, again, in absorption and emission. So we can begin to understand the chemical composition of these stardust grains. And there isn't, by the inclusion of ethene there, you can tell there isn't just dust. There are also molecules formed in the outer layers of these stars. And so these billowing clouds don't just contain dust, they contain lots of molecules. Here's one of the biggest stars known. It's about 100,000 times more luminous than the Sun. It's several times more the radius. It's I'm trying to remember its name now. Really famous one that I've forgotten. VY Canis Majoris, that's it. Again, it's got a large cloud of material just buffeting off the star. You take an infrared spectrum, you have the signature of all kinds of exotic molecules, silicon monoxide, carbon monoxide, a lot of steam, water, hydroxyl, and this underlying infrared light is due to the dust grains. So the dust originates in stars. It's puffed off the stars in these large clouds, and it kind of expands away into the interstellar medium. But the way it's really liberated is when these stars reach the end of their lives and explode. So, for example, they may form a planetary nebula. This is what happens to a star like our Sun when it reaches the end of its life. It runs out of fuel at the core collapses, shrinks down. It's no longer producing energy by nuclear fusion, so gravity wins. The centre of the star collapses down, heats up. Because if things fall into gravity, they heat up. And this heats up the outer layers of the star, which then are blown off in a nova event and expand away. And you get this expanding shell around the white dwarf. Because the white dwarf is heated up, it can pump out energy into this gas and it can cause it to glow. And you have this expanding ring that moves away. And so for a few thousand years, you get a structure like this. This is the Ring Nebula in Lyra, which is a planetary nebula. The different colours are due to different atoms within the gas glowing their characteristic colours if you pump energy into them. But I'm less interested in the gas because I want you to note there are obscuring features within the shell. And these are dust, perhaps dust that's been blown off previously or that's actually and is now being mixed in with the expanding gas, or it's dust that's been blown off with the gas. And this shell will expand away over the next few thousand years and eventually become mixed into the surrounding interstellar medium. And many of these planetary nebulae show these dust structures from that unstable period as a red giant before they exploded as novae. Here's a nice example. This is the Eskimos' Head Nebula. So there's his face, and you've got the fur parka around the outside. But the fur parka is actually dust. You can sort of see streaks out like that. They've had a blast wave that's gone through, and you've got dense knots of dust structures. You have the Cat's Eye Nebula, where you have up to 11 concentric bubbles of dust that have been thrown off by the star for about 1,500 years before it eventually collapsed down to form that white dwarf. And it's also produced winds and jets and all kinds of spectacular things to produce this structure. And the dust can be directly detected, again, if you move to the infrared. So here's the Helix Nebula. It looks like a shell, but it's actually a bit more like that. And you're just looking down the helix structure. If you move again to the infrared, you will see just the light from the dust surrounding that. And so this is our main source of dust. And that also tells us why it's confined to the plane of galaxies, because it's within that spiral arm that you have all the really active star formation. We see it most obviously from the bright clusters of blue stars, but there's lots of ongoing star formation. And certainly the more massive stars go through quite rapid life cycles, and they will generate a lot of this dust, and it kind of accumulates and gets squeezed together and compressed, and it's embedded within these clouds. So you have dust that's generated. So one final effect of dust I want to show you just on an exploding star. This is the Butterfly Nebula. Again, it's a nova, a star that's blown itself apart at the end of its life. But it's not that nice spherical shell that we've seen, because an earlier explosion of dust from the star in its unstable red giant phase has produced some kind of obscuring torus here. That's why we can't see the white dwarf at the core. But that's also affected the outflow and confined it into this bipolar shape that gives us the butterfly. So there is dust everywhere, and you see it by obscuration in the optical. You will see it mixed in with the gas. And so you'll have the pink glow of the hydrogen gas that's being excited by the stars, but mixed in with that you'll have the dark tendrils that are blocking out the background light, and very often the neighbouring reflection nebulae. And this is the case here in the Trifid Nebula. You've got dark clouds of dust and then reflection, and it's all mixed in together. So where you have the dust mixed in with the gas, you get it in varying amounts of mixture. Sometimes it's quite diffuse and you can't even tell it's there. Sometimes it's very obvious. So here's an example where you have an Emission Nebula. There's a young star cluster here, maybe a few million years old. They're pumping out lots of light that's heating up the background gas within the surrounding clouds. They've blown a cavity around them with their winds and their ionization. But within that cavity, there are knots which are far denser and resist that erosion. In the same way that Horsehead Nebula was stuck above the surrounding cloud, because it was denser, it was resisting the erosion from the winds. So here, for example, silhouetted right across the front of the nebula, you have completely opaque knots. And these are the densest pockets of the cloud. It's where the dust is mixed in with the gas to form the densest regions of the interstellar medium. I mean, we wouldn't call it dense. It's nowhere near as dense as the air we're breathing. It's relatively sparse, but it's still the densest regions of the interstellar medium. And there's so much dust there that these are completely opaque. And not just that, but because they're blocking the starlight from travelling through the cloud, the dust on the outer parts of the cloud are blocking the energy and the heat from the stars from entering the core of the cloud. And so right in the core of these densest clouds, it gets incredibly cold. There's no internal heat source. You're only a few degrees above absolute zero. And at those temperatures, you're going to have the atoms joining to form molecules. So it could be, most commonly hydrogen molecules. But there's a whole slew of exotic, mainly carbon-based organic compounds, from formaldehyde to ammonia, carbon monoxide, ethane, methane. They're all discovered within these very dense knots. And so these are also known as molecular clouds. They're getting broken up by the starlight and the star winds. And so you can see, for example, this one ends up having quite jagged effects and quite jagged shapes. This would gradually get eroded until you've got just these very dense pockets or knots left. And we tend to call these globules. And here's an example of one of these clouds that's been completely shredded. And you have these cold, dense, opaque knots. And they could be of sizes of, say, from a few to about 50 light years across. And there's enough matter in one of these clouds to, again, it depends how dense it is, but it could be up to 1,000 Earth masses of material, or even solar masses of material, embedded within that cloud. And here's where the dust is important, because it's providing the ideal place for star formation to occur. Because dust is mixed up with the interstellar medium, it becomes part of the ingredients for the star formation, but it also makes these knots, these globules, the prime place. And the reason for why star formation occurs best in these is because if you have a cloud of a given size and a given temperature, whether or not it collapses under gravity depends on how dense it is. To collapse under gravity, you just need some particles, maybe these ones and these ones within a cloud, to be slightly closer to each other, to feel each other's self-gravity a bit more. They'll start to pull towards and form a slightly more overdensity. And then that has more mass, it's got more gravity, it exerts a stronger pull on its neighbouring particles, and it'll pull more of those in, and you begin to get a runaway sense of collapse. However, we know there are lots of gas clouds out there in space that haven't collapsed under gravity, and the reason is probably because they're too hot. Because the one thing that can resist this inward pull of gravity is, of course, not all the particles just stay there and wait to be pulled on by gravity. They're moving around all the time. Temperature is a measure of the average energy of particles in a cloud. And so even if they're only just a few degrees above absolute zero, they're moving around, they're jiggling, and that jiggling can resist the inward pull of gravity. And so for any one cloud, you have a balance between this outward pressure of all the motions of the particles and the inward pull of gravity. Okay, is everyone mesmerised yet? Yeah, good. And so you can see whether or not a cloud collapses depends on the balance between, gravitational force versus the outward thermal pressure. In other words, density is more likely it is to collapse under pressure and collapse under gravity, and temperature. Cooler regions moving around less resist the gravitational regions, force less. And so within any diffuse cloud in the interstellar medium, it is the coolest, densest regions that collapse to form the stars. And of course, those are provided by those opaque knots. So when we go to these nebulae, those very opaque knots are where star formation is occurring. Let us return to the Orion Nebula. Those of you who came to my rotation lecture may have seen some of these slides before. Because in the Great Nebula of Orion down here, this is 1,500 light years away, you can see that the whole of Orion is encased in this gas and dust. And in fact, we were looking at the Horsehead Nebula earlier here. This is Orion's Great Nebula. And what you have to realise, it's part of a giant molecular cloud. This is just one corner where there's a young star cluster in, it's excavated winds, and it's blown a cavity which has just burst in our direction. We call these blister nebulae. And we are privileged to actually just be able to see inside that cocoon and see this region of gas and dust. So imagine this is a large bowl. And again, if I just zoom in on this region and show you the Hubble Space Telescope picture, okay, beautiful. You get the idea of these tendrils, these wisps of dust, and how perhaps they've been pushed around by the winds of the stars. And just to give you an idea of what that looks in the infrared, here we are. You can see that there are, in fact, many more stars embedded in here. And the interstellar medium wasn't kind of uniform, so it's preferentially kind of gone off and blown the bubble in one direction rather than particularly around them. So this is a very dense region. Now, if I zoom into around the 4 stars in the centre, these are called the trapezium. You can see them through binoculars. And this is going to be a bit bright, so I just change the contrast a little bit. We're going to go back and look at some of these features. And these are what those dense globules, those little knots of really dense cold gas and dust go on to form. And these are called proplids, protoplanetary disks, and these are what mark areas of new star formation. So you have this very dense, dusty globule, very cold, it's dense, but it starts to collapse under gravity. And the process of star formation, you have your cloud, it's denser in the core or somewhere within the star. Maybe the cloud will fragment and form lots of stars, but you have one region that's overdense. By gravity, it pulls in matter from the cloud. Matter rains down towards the centre. If things fall under gravity, remember they heat up. So the centre of this cloud begins to get warmer and warmer. And material keeps raining down and accumulating in the core until you reach temperatures of, say, 15, 20 million degrees. At that point, nuclear fusion is triggered, the star starts to burn hydrogen to helium, and you've got the protostar formed at the centre of the nebula. But you still have the remains of this cloud. It's no longer going to accumulate matter, but you've still got all the remains of that dusty globule surrounding. It's collapsed down under rotation. And you have this cocoon surrounding the star that is rich in dust. And you can tell it's because of the way it obscures the light of the star. So again, this is just an artist's impression, but where you have the protostar in the centre and a thick obscuring cloud, which is very heavily concentrated in that dust. And it's those disks which will go on and form planetary systems. Here are examples of some of the ones in Orion, where again you can see at the centre the obscuration by just showing how thickly these are packed with dust, and some of the protostars right at the centre. Of course, it is arguable whether these proplids in Orion will go on and form planets very much like our own solar system. They're really in a harsh environment with all these winds from the massive stars. And indeed, if I go back to these 4 stars at the centre and just ring the proplids and give you an idea of their dimensions, they're all kind of being blasted out, almost like little windsocks. And it's quite possible that these proplids will go on and form a solar system with only just a few tight planets around a star, and anything that would kind of be Neptune dimensions has long been stripped off. And so maybe these aren't very good cases for what our own solar system was like at this time. But nonetheless, it was a good model for what happened to us, 5 billion years ago. The sun had formed, you've got this dense cloud of material. So within this dense cloud, you have particles of dust. And these are the seeds from which the planets form. Now, we can't see this process in detail because it's buried in a thick, dusty cloud. This is why we need the James Webb Space Telescope, to be able to peer into these proplids and see the process of planetary formation starting to happen. We can see some of the early stages, for example, nearby stars. So this is a garish false colour picture. There's a really bright young star in the middle, and they've masked it out because its light is too bright. And this is an infrared picture, and you're showing the infrared light reflected off what is a thin disk. So this is one of those cocoons. A few million years later, it's collapsed down, it's thinned out. And the material within that disk is beginning to clump together to form planets. Now, give you an idea of scale, those original cocoons are probably about 10 times the size of our solar system. They tend to thin out and flatten out, and so when you get to this kind of debris disk, as we call them, you're looking at something, here you're looking way out beyond the orbit of Neptune in our own galaxy. Because the glare from the central star is so bright, you can only really see the extremities of this debris disk. And here, the fact that it's slightly skew, you can see there's more light here than there is here. It's all kind of bunched up. I mean, there are a number of these debris disks that people study. And you can see from the asymmetric distribution, you think maybe there's a giant planet forming somewhere in there. With some of them, if you analyse the way that the infrared light is reflected or polarised, you can begin to tell properties of its size, perhaps, of the dust within these clouds. And so, for a similar system in microscopium, you get the nature of the reflected light tells you that out at the edges of these like pre-solar, pre-planetary disks, you've got very light, fluffy aggregates of dust grains. And we think what happens is the star at the centre, it's got lots of stellar winds and what have you. Very young stars are very unstable until they get their act together about how much energy they need to produce at the core to withstand gravity. There are lots of stellar winds that can push particles out. And this has an effect on what kind of planets form. So within the dusty nebula, you have dust grains that start to stick to each other, perhaps through electrostatic forces, and they just kind of accumulate and they just kind of grow, and you get little fluffy aggregates of grains. And once these get over a certain size, they become the overdensities that pull other particles towards them through gravity, and they grow bigger and bigger. And eventually you get to a period where you have what are known as planetesimals, small planetary, subplanetary sized bodies. And there are lots of them within the solar system. Now, obviously, this is an artist's impression, but it gives you an idea that you have a lot of debris going around. Because these planetesimals will then collide with each other and form protoplanets. There's a lot of, there are too many of them. They either smash to smithereens and generate debris. This is why we call this debris disk, which is then blown out by the winds of the star to further out in the disk. Or they stick together and start forming some of the planets. And so there's a lot of junk around, if you like. A lot of this stuff in the early solar system that gets blasted out to the outer edges of the solar disk. And as I say, it affects what kind of planets form where within the solar system. So close into the young sun, strong winds, all lighter elements like the hydrogen and helium get blasted out to the further regions of the solar nebula. Further away from the sun is cooler. It's less intense. And so the smaller rocky planets, the things that involve silicates that grow directly from the dust, are the inner planets. By the time you get out towards sort of Jupiter and Saturn, you've got the silicate core, but you have enough lighter elements that they can grow these deep atmospheres over a period of time to become the giant planets. And then by the time you get to Neptune and Pluto, the process is slower. Things are moving more slowly. Further out they are from the sun, they have less time, they're unable to accumulate as much mass in the same amount of time, and by the time you get to the Kuiper belt and the dwarf planets, you don't have large planets building up because there isn't time. Things don't actually encounter each other enough to either collide or stick together to build really big planets. And then a few million years after it starts, the sun kind of sweeps the inner parts of the disk clear of all this dust, and a lot of it goes to reside in the outer edges of the solar system. So we include cosmic dust as part of our solar system. Now, we can find out about this because it's brought to us from these outer edges of the solar system by comets. There's a cloud of comets way out at huge distances, way out beyond the Kuiper belt, even several thousand times the Earth-Sun distance, or tens of thousands times the Earth-Sun distance. You have material that was really cold. It's out in the deep freeze of space. This is where the comets form, mainly from volatile compounds, from ices. But included within those ices are dust particles, and they are encased and entombed within these snowballs. And the nice thing about these dust particles is that they've never been part of planets. If things part of a planet, it gets heated up, it undergoes geological processing, it gets fundamentally changed. Out in the deep freeze of space, it's not completely pristine, but you have samples of that original cosmic dust that was in that solar nebula that condensed from that interstellar medium. And so by looking at what's in the comets, we begin to sample the ingredients of that very early solar nebula. Now, as the frozen snowball, if it gets perturbed from its position out in this giant cloud, it begins to fall towards the sun, it gets heated up. Here, for example, is a picture of Halley's Comet. You've got the original snowball, which is about 10, 15 kilometres across, and then you have what's called the coma of material outgassing, because the ices begin to sublimate. In other words, they go straight from solid to gassy as they heat up. And you get cracks opening within the snowball of the comet and outgassing of the icy volatile compounds, and with them they take the particles of dust. And so that generates one of the tails of the comet. This is made of charged particles, good ions, but the sort of longer curved tails of a comet are the dust particles that are brought out of the comet with the gases. And they shine by reflecting the sunlight. And so one way that you can sample cometary dust is you go and meet a comet. So the Stardust Mission was a little robotic spacecraft which was launched in 1999 to go and rendezvous with Comet Wild in 2004. And here's its picture of the nucleus of Comet Wild. You can see it's kind of pitted and it's got interesting structures. And now this was quite a way out from in the solar system, so it hadn't yet started particularly outgassing. There were a few cometary particles. It's beginning to outgas, but it hasn't got that enormous coma and tail. And little stardust flew through the coma, through the stuff that's being outgassed from the comet. So here's a picture from it as it goes to sort of rendezvous with the comet. So it just flies past. And as it flies past, it's got a little tray that it exposes. And this tray is made of, it's got pockets of what's known as aerogel, a very light, porous substance. And it just sweeps up particles from the comet and captures dust particles. And so these get embedded in the tray. They're travelling at high speed, or the relative speed of the spacecraft and the comet is incredibly fast. And they bury into the aerogel and they score these long tracks. So there's the point of entry. And they've got so much energy, they shoot right through the gel and come to rest. And at the end, you've got the dust particles. And the reason I know what they look like is that after flying through the comet's outgassing, they sealed up that tray, which was then brought on a sample return mission to Earth. And so they can examine these dust grains in the lab. This is the sample return tray in the lab after it's parachuted through the sky and burnt up through the atmosphere and landed somewhere in the desert. So you can begin to examine some of these dust particles that have been carried from the outer parts of our solar system and see how representative they are of those other dust particles we see out in space. And what you find is that they're broadly compatible with the outer regions of some of those debris disks. And so again, that's matching what we see around other stars to what we think goes on in our own solar system. And that, for example, is a nice particle of stardust brought by this Stardust mission and captured in those aerogel. But then, if you wait long enough, you might even get more of this stardust. All the dust that's being gassed off from the comets settles towards, first it starts to follow its own orbit around the sun, and then it gets scrambled by gravity, and eventually you get this kind of thick dust within our interplanetary medium. So it's stretching out from about Mercury out to about Jupiter. You've got this flattened distribution of dust, which is mainly invisible, but is sitting there between the planets. If you're very lucky, you can see it in the night sky, either just before or just after sunrise. Now, this is called the zodiacal light, and it's a triangular, very faint glow. It's one of those things where if you look at it directly, you don't think you can see it, and if you look with averted vision, you can maybe see it. And that is reflected light from the sun, and it's just illuminating that sort of flattened disk, and it'll follow the same track that the sun and the planets follow in the sky, called the ecliptic. So that's evidence of that dust, which is also telling you that there is dust out in the interplanetary medium. Well, we are on a spaceship Earth. We don't have to send spaceships to comets to pick up interplanetary dust. We ourselves are sweeping through this cloud. And every year, several tons of material, many, many tons of material fall onto the Earth. And so we can actually collect cosmic dust. Here are some particles, again, back where I showed you at the beginning. Most meteorites, if they fall through the atmosphere, they will burn up, unless they are really small. So if they're less than about 100 microns in size, it's possible that they can be slowed in our atmosphere without melting, without burning up, and they can more or less float down to the surface. And these are called micrometeorites. And so we are very well placed to detect cosmic dust arriving directly to us on Earth. So an awful lot of the dust you have around you, there is within it a large amount of cosmic dust. Collecting it is a challenge. There are many ingenious ways of doing it. They have collecting plates that fly into the wings of stratospheric flying aircraft, where they go and scoop up some of this cosmic dust directly from the atmosphere. Other inventive places to collect it are in deep-sea ocean sediments, or places where there aren't much dust, so like some of the ice masses at the polar ice caps, and they can collect good samples of this cosmic dust and begin to study it and compare it to what we see out in space and also what we see from the cometary dust, and begin to map out also where these particles come from within the original solar nebula, and therefore how it differs within that original solar nebula, how the effect of the young star affected the dust particles from different parts. And then, of course, you don't just get individual grains of stardust, you do actually get little pockets of stardust within larger meteorites. Here's a picture of, just excuse me, I meant to get something out earlier, of something called a carbonaceous chondrite. I've got one here if anybody wants to come and look at it afterwards. And this is a stony meteorite. These are relatively rare. It's about 5% of all stony meteorites. And if you look closely at them, they have little circular marks called chondrules, these things. And these are molten drops of stardust right from the outer edges of our solar system. So these are some of the most pristine parts of stardust that you can have, which have later been incorporated in some of these asteroidal bodies from far out within the solar nebula. And you can tell that they're quite pristine stardust in terms of the isotopic composition of the elements, in terms of how the kind of combination of organic and volatile compounds they can compare. I don't want to get into a chemistry lesson, but basically you can test the components of these chondrules and find they will match the outer areas of some of these nebulae, and indeed match well the stardust that we find in the interstellar medium and in the nebulae. And so when you hold something like this, you're holding actual particles of stardust which predate, of course, the formation of our own solar system and our own sun, which is a pretty nice note to end on. So, just to say this is my last lecture this year, advance notice, these are some of the things I'm hoping to cover next year, and look forward perhaps to seeing some of you then. Thank you.
For all information, please visit www.gresham.ac.uk.